What's good, everyone? Welcome back to another video. For this video today, we're gonna be talking about heap. And so, what is a heap? Heap is a special kind of binary tree used to quickly get the min or max element. So, if I were to write it down, heap, special kind of binary tree. There we go. And keep in mind, this video I'm only talking about heap and not heap sort. So a heap is a special data structure, while heap sort is a sorting algorithm that uses heap data structure to organize a list of elements into sorted order. So heap is a tool. And the heap sort is a process that employs that tool to achieve a final sorted date array. Okay? So, keep in mind for this video, I'm talking about heap only for data structure, not heap sort. But who knows? Maybe on the next video I'll do heap sort or whatever. But technically I'm focusing on mainly just the data structure stuff, so not the all the algorithms yet. So Okay, so there are two main types of heap. Two main types. We have the min and the max. In the max heap. So min heap, max heap. Min heap is the smallest value is always at the top or root, whereas the max heap is the largest value is always at the top. Okay? There's also two important properties that you have to know. So two properties. We have the shape property, shape P, and heap property, or heap P. P short for property. For shape heap, not shape heap, shape property, it's a complete binary tree. So all levels are fully filled except possibly the last one. And then the last level is filled from left to right with no gaps. Okay, so sort of like why does these two like properties even matter? You have to know, and like let's first take the shape property first. We care about that because it guarantees like a small height, which will give us a big O of log n property, or operation. Sorry, so big O of log n operations, because a complete binary tree with n nodes. A complete binary tree with n nodes has height that is about the height of h that is about log n. When you insert or remove a certain value or element, you only move up or down the tree along one path. So moving at most h levels will give you big O of log n work. But if the tree wasn't complete, then it can become just basically a very tall tree, or like a tall and skinny tree, right? Or like skewed. And when that happens, the height could be big O of n. And then when you want to do something like insert or pop, then that operation becomes big O of n, which is not ideal. So you wanna keep in mind that that the shape is very important here, because it can make, if there's no shape, it can make the heap become like as bad as a linked list. So keep that in mind. And then for heap property is talking about like the parent versus children. And so for heap property, it is about where each node. So let's say for the min heap property and the max heap property, for min, each node has to be less than or equal to its children. Its children, not children in general. And then max is the other way around, where each node has to be greater or less than its children. Okay, we care about this because root is always going to be min or max. Because every child is, let's say for min, every child is basically greater then its parent, the smallest value is forced to bubble to the top or move to the top. So when you call in like an operation like peak, for example, then it will always be big O of 1. And it will always be correct. And so when we insert or remove, we might, and another thing is, if we want to insert or remove a value into it, there's a good chance that we might break the heap property in one place. And to fix it, we only need to compare with the parent or child and swap when it's needed. This way, we don't need to like resort the whole structure. And that's why the heap property also matters, because then when we do something like the operation like insert or pop, it's going to be big O of log n as well, and not something like big O of n log n. Okay? So, best way to say it is, let's say for the properties, you have, if it's only shape, then that means only shape and no heap property. That means it's a balanced tree, but you can't guarantee that the root is going to be minimum or maximum. If it's heap property only and no shape, that means the root is correct, but the tree could be extremely tall. So when you insert or pop, it becomes big O of n in worst case scenario. So just keep that in mind. That the two properties are important here. Okay, yeah. And also, another thing to know is that this is not a BST, binary search tree. Because the left child doesn't have to be like less than the right child. So normally when I draw the trees, I would draw like this as an example. This would be the min, by the way, because the root is the minimum, while everything else is, when you compare 1 and 2, the child is greater than the parent. When you compare 2 to the 2 to its child, the child is greater than the parent. So this would be the min property. But keep in mind, in a heap, let's say the 2 and the 3 for the node doesn't matter. Like, their order doesn't matter. Heap only cares about parent versus child, not sorted order across the sibling. So these matters and these matters, but 4, 5, 3, and 2, they don't matter. The order does not matter for those. So there's that. Now, how do we store a heap from like an array view? Okay, so array view, store a heap. Okay, so for this part, it's like, you want to know that heaps in real code are just arrays, not pointer trees. When we draw a heap, we draw it as a tree. So for example, something like this. But in almost every like real implementation, the Java, like in every real implementation, like Java priority queues, it's actually just array. So you would have the index, which is 0, 1, 2, 3, 4, and then the value, which if we write it down, it would be 2, 3, 5, 10, 8, like that. And the tree structure is implied using the index formula. And I'll write down the index formula. So left child of I is basically 2 times I plus 1. Right child of I is 2 times I plus 2. Parent of I is I minus 1 over 2. Okay? So, you just have to know, and you have to, this is basically sort of a way to understand, like, how am I going to be able to insert, like, new values into it, right? But for now, just know that this would be an example of heap as a tree, but what matters the most is this part, because this is the array representation. And this is why heaps are like very efficient, because it's not pointers, but just index math. All right, so let's do some core operations. So core operations. And we're gonna be doing this on a min heap, by the way. So min heap. Let's do the first one, which is insert, or you can say push. So our goal is insert X and still keep the heap property. Okay, so here are the steps. Our first step is put X at the end of the array. Here we go. Our second step is what you call like bubble up. Okay. This part doesn't matter. Or I mean, like, you don't really need to call it bubble up, but like that's how I was taught in a way. This part doesn't matter, okay? This thing, what doesn't matter. What matters is like what you gotta do. The naming wise, don't even worry about it. Okay, so while X is smaller than its parent, keep in mind it's min heap, so smaller than its parent, swap X with its parent. There we go. And then you stop when parent is smaller or equal. Because when it equals, there's no point of like swapping it since they're the same. But if the parent is smaller, that means like you can't swap it anymore since that'll break the min heap. So there's that. Or we reach root. All right, so let's do a quick example. We're gonna have a tree with 2, 5, and 8, and then we're gonna have the array. And I'm gonna write the index out too. So index in value, index 0, 1, 2, 2, 5, 8. Okay, now we want to insert a value, and let's say we're gonna insert 3. So when we insert 3, we insert it here. We add a new index, which is 3, and then the new value, which is also 3. Okay, so 3 is at index 3, and we're going to do the parent index. And that has its own equation, which was I minus 1 over 2. So what we have to insert is the I, which is index. So when we have the value 3 is at index 3, so we got to insert that. Oh, we're inserting this, by the way. Not the value, but the index of 3. So this becomes 1. This is index 1. So when we look at index 1, we're looking at 5. So the value is 5. We get the value, which is 5. And now we're going to compare the 3 and the 5 value, right? The value 3 and value 5. So this is the part where we're going to check the bubble up thing. So is the 3 smaller than its parent? Yes, it is. It is smaller than 5. So what do? We swap X with its parent. So we swap 3 and 5. So now it becomes 3 here and 5 here. So once again, we swap it. Oops, why did I write 5 again? 3 and then 5. There we go. So there's that. Now we look at the new index of 3 is, so here's a 3 value, and we want to look at its new index, and that one's 1 this time. So instead of 3 for the I, we're going to change it. We're doing parents index again, but this time it's not 3 for I, but 1. So 1 minus 1 equals 0. 0 over 2 is also 0. Okay, so now we look at the index 0. And what value is that? That one is 2. And we do the same thing. Is 3 smaller than its parent? This time, it is not. 3, the parent is actually smaller than its child. So when that happens, we stop. And that's it. That will be the final heap. This will show you basically the very final heap. And so, there's that. Now let's do a remove, right? Remove the root, which is the minimum, and then fix the heap. So let's say we want to do remove min, or basically pop. So the goal of it, remove the root, which is the minimum, and then fix the heap. So the steps for that was, first, you want to save root value, because this is what we have to return first. Or basically, in a way, is like, this is what we return. Move the last element to the root position. Remove last slot. This way it shrinks the array by 1. And then finally, you want to do this thing called bubble down. So there's bubble up. This time it's bubble down. Now for bubble down, we have while current node is greater than one of its children, swap it with the smaller child. Damn, that's a lot to write. Holy cow. And then stop when it's smaller than both children or no children. Okay, sorry for it to be kind of a messy thing. I was not expecting it to write a whole page like this. Okay, but again, let me go on to a new page this time to continue. Oops, let me go back. There we go, a new page, and we're gonna continue with our previous heap, right? So we have a 2, 3, 8, 5. Here's our index. 0, 1, 2, 3. Value 2, 3, 8, 5. Let's just copy this part. Well, oops. Yeah, we gotta copy this whole thing. God damn it. What do I copy again? There we go. Oops. Alright, there. We're gonna paste. Nice. Okay, so remove min. Remove this. Remove this. And then now move the last element, which is 5, to the root. So move 5. Dang it. Move 5 up here. 5 over here. Okay, so when that happens, this is gone, and this part is gone. Oops. Boom. Boom. Okay. Now, oh, and keep in mind, we're going to move the last, remove the last slot. So now this is gone, and this part is gone too, okay? Jesus. All right, there we go. Now we're going to do bubble down. So bubble down from root, with 5 has its children's 3 and 8. Now, when you look at it, or when you do it basically. So while current node is greater than one of its children, which it is, you want to swap it with the smaller children. So 3 is the smaller, and so you want to swap 5 and 3 because 5 is greater than 3, so you swap it. So when you swap these two, then it becomes 3 and 5 over here. Now 5's children doesn't exist, which is leaf. And when that happens, you're on this part. It has no children. And so you stop. So now the final heap will look something like this. This would be on a tree, and then the array is already done. So there's that. So now you still have a valid heap. And that's basically the gist of it for just, the very basic of the operation. All right, so finally, we're going to talk about the last things, which is time complexity. Time complexity, and we're going to say let n be the number of elements, height h to be the height of the heap, which, by the way, is gonna be log of n. So when we do something like insert, bubble up at most height, big O of log n, remove either min or max, you're gonna bubble down at most h, which again, it is big O of log n. You wanna peek the min or max, you just look at the root, so that's big O of 1. And so this is sort of like why heaps are used for, like getting top n element, not n element, because I already said n is the number of element. So let's say top k element, things like priority queue, that's very good because always process highest or lowest priority next. Dijkstra algorithm, shortest path, that's something we can talk about. Other things like merging, sorted lists, and things like that. So just keep that in mind. The video's gone long enough, so thanks for watching. Thanks. Bye. If you want to see another side of me that isn't always about computer science, then check out my other YouTube channel and come and watch my Twitch where I play a bunch of competitive games either by myself or with my friends. And not only that, but I do have my Discord available just in case if you wanted to add me either to just talk about anything, whatever you want, or have some kind of question from my video. Thanks.